First of all, let me introduce myself. I'm Gabriel Elkheim. I will be your torturer, tormentor, and instructor for the next 10 weeks. I say that a little lightly. So how many of you have no idea what this class is? Anyone? Okay, one of you. All right. So good. So my reputation is firmly established, which is good. This class is two things. One, it's a ton of fun, and two, it's a ton of work. All right, and both of those go together. It is, I will state unequivocally, the most time-consuming class on this campus, bar none. All right, you will spend more time doing this stuff than anything else you probably have done in your entire lives up to this date. We will cram more knowledge into your head in the next 10 weeks than you ever thought possible. And along the way, you'll learn lots of things about yourself that you never knew before. You know, how well you work under really, heavy stress, how long you can go without sleep, how long you can survive on ramen noodles. This is a good one. Anyway, all that joking aside, this is an intense ride. Okay. Now, if you stick with it and you do the work, all right, what I promise in return is that it will be a learning experience unlike any other you have had. Okay. By the end of it, you will know a great deal. You will have sitting in front of you a robot that you have built that does something without you touching it. And that is pretty cool. All right. Now, at that point, you may not be awake enough to recognize that it's pretty cool, but surprisingly, after you've slept, you sort of have this fuzzy sort of memory that it was kind of fun to do. Anyway, these are very valuable skills that you will be learning here. There is a long line of people hiring students out of this class that basically all they ask me is, did they do well in this class, period. No other questions. Not that they graduate, not what degree they have, not what their GPA was, not if they're easy to work. Did they do well? That's all they want to know. All right, so we're going to go over just sort of a quick amount of background here. So smart products, as they're sometimes called, so the idea is that we are going to focus on a microcontroller or a microcomputer, depending on your flavor, but as a component, not as a controller. So that's to say, if you want to learn to make a pendulum stand on its head automatically or do any of these sort of feedback control system class, this is not that class. Right? That class is CE 241 or CE or EE 154 or CE 154, I think. If you want to take that class, go right ahead, but that's not this class. All right. So in this class, the most sophisticated control we're going to get is basically on or off. All right. So it's not very sophisticated. You'd be surprised how much mileage we can get out of that. So it encompasses things that are commonly referred to as mechatronics and also embedded system design. All right, and the reason why, anybody have any idea why the microcontroller has come to reign supreme as a component inside all these systems? A guess. Yes. Easy to use, not really. Get your average person to try to program a microcontroller, they're not going to do it. Engineer, yes. What's that? Cheap, that's it. That's the answer. Right? Cheap, cheap, cheap. All right, so Intel may rule the roost in terms of, the microprocessor that you have inside your various laptops and tablets. But if you want to know what processor is deployed farther on, it's a little 8-bit jobby that Motorola makes that, there's about 8 of them inside every car engine manufactured. All right, and so they're all over the place. And the idea is, in terms of volume, they swamp the desktop market. And nowadays with cell phones, you're getting kind of a little bit of a crossover because, this one's got an ARM7 in it. All right, so they're everywhere. And the idea is, because they're so inexpensive, it's often cheaper to put a microcontroller in than it is to put even some kind of digital logic or a switch or something like that. If you can put the microcontroller in, then things work, and they work well. All right, so what makes it different is basically you get some intelligent decision-making. Decision-making. All right? And what that means is you have the ability to adapt and to react. All right, so sometimes these are called reactive systems. All right, and these are, and the reason that's such a big deal is because it becomes cost effective. Bless you. All right, so as an example, consider something as simple as a chairlift. All right, so here we have, there's the top of the mountain, right, and so you have your chairlift that goes around. Now, the old days that these were made, all right, they had, the chairlift, a big motor, big giant relays, a varistor that they could turn that could sort of set the speed of the thing, the big red kill button at the bottom and the top, the slow start button, and all of this was done with big, giant, heavy power electronics. All right, expensive to build, expensive to drag up the mountain, expensive to install, very expensive to maintain, but reliable. They worked really well. They almost never fail, which is a good thing. Problem is, when they do, right, you've got to sort of get a tractor to come up to the top of the mountain to bring the next one with you because it's big and heavy. And you have another problem, which is, so you've been doing well, you've studied, and you decide, you know what, my chairlift is too slow, I want to run it faster. All right? All of a sudden you're like, well, now I got to redesign everything, which means that they're not very flexible. All right? You can't change them easily, right? Which means you're sort of stuck into them. Then, more modern things, they use something called a PLC, a programmable logic controller. Right? And a programmable logic controller are these sort of big industrial boxes. If any of you have heard of the Stuxnet virus, any of you? Yeah, a couple of you. Okay, so those were doing PLCs, by the way. So PLCs are kind of used in industrial control everywhere. They're still cumbersome, kind of archaic, difficult to use. And so these days you say, well, let me throw in a microcontroller to it. I can, for instance, measure things that are happening in real time. I can measure the tension on the cable. Right? I can react to wind loads. I can have a wind sensor up on top and say, hey, the wind gets pretty high, I'm going to start slowing down automatically. Right? I don't need the operator to sit there and decide to slow down. I can just slow down because as the wind is starting to gust, it's telling me that, it's going to be an unpleasant ride for the people. I need to slow this down. Right? Consequently, I can sort of, if I add more chairs or if there's a snow load, they get heavier. Right? This is going to affect how much current I need to push into the motors. Again, I can adapt to this automatically. I don't have to have someone constantly sort of watching to see whether it's going slow or fast and adjusting it accordingly. So it gives me this flexibility. And the flexibility is key. It keeps us going well. All right, so moving along, what makes the decisions? Anyone? What's that? CPU, well, let's call it the computer. All right. So the computer, and what does the computer operate on? What's that? I/O? Not really. Keep going. Yeah, too abstract. Fundamentally, what does a computer do? What's its name? Right? A computer computes. What does it compute? Numbers, right? It operates only on numbers. Right? Operates on numbers. That's a subtle point, which means that anything that you want it to do has to first somehow get translated into a number, right, so that you can do something with it. Right? This is computers are dumb, right? On the other hand, so one of the ways to think of a computer is it's a very diligent but obtuse and in some ways perverse servant. All right? So it will do exactly what you tell it to do. Not what you wanted it to do, but exactly what you told it to do. You get to boss it around a lot, though, which is to say it never talks back. It doesn't actually, say no. It'll do it, all right? But it'll interpret what you want it to do precisely, and it's kind of dumb, which means that, for all the quote-unquote intelligence in it, computers are pretty stupid, all right? They do precisely what you've told it to, and you have to tell it precisely what you want, and if you don't, it does what it thinks you told it to, not what you thought you told it to do. In fact, that's most of our debugging. Most of our debugging consists of trying to figure out what we actually told it to do by seeing what it did versus what we thought we had told it to do. All right, so there's that ambiguity that we have to resolve. Okay. So where have you encountered anything? I'm going to futz with this a little bit for while you guys spitball some answers at me. So what objects do you guys know that have little computers embedded in them that make it work? What's that? Sorry. Coffee pot, indeed. The modern ones certainly have a coffee pot in it. All right. What's that? Cars? Cars have a ton, right? So I've seen one thing that one of the Mercedes, damn, I was hopeful. One of the Mercedes ones had the chair on one of the Mercedes models, I believe, had, yeah, we're good. Okay. So I'm just going to hold this like that. What we do, okay, so we've got cars came in. So one of the Mercedes, I know just the seat, the passenger seat, I believe has 16 motors and 4 microcontrollers in it. Yeah, I think it might order out for pizza for you, but I'm not sure. Kitchen appliances, that's another one. So lots of those. All right, what else do we have? Anything else you guys can think of? Yeah. Not a lot of them. The flashlights tend to be still on the stupid end, where they're literally just a switch, and it connects it straight to the battery. Some will sort of blink and pulse and do something like that. Those will, but yeah. Yes, televisions most definitely. In fact, televisions, we are at a point of kind of bizarre levels of complexity in terms of getting content to you over the television screen. Right now there's like 18 different ways to deliver media to you, and no one knows which one's going to survive or do that. The whole market's in utter chaos. But it's kind of cool from our perspective because you can do neat things with it. What else we got? Anyone? Yeah. What's that? Yeah, so phones, telecom, so phones, especially cell phones, have long since become a different item than they used to be. Yeah. What's that? Yes, missiles, aircraft, most definitely. Missiles, aircraft, spacecraft. All right, all have a ton in them. Let's see, anything else? Obviously, your MP3 players. The other one, medical devices, huge, right? So a lot of what you will do if you go on in this thing, medical devices. So medical devices are a pretty neat field. They've got some pretty stringent requirements because you have to make sure you don't kill the patient when you make a mistake, and you laugh, all right? But they have. All right, there's a very famous machine called the Therac 25, which was a radiation machine built by GE, and it was built a while ago. It was programmed in assembly, and it was meant to treat people with brain cancer, and so it would sort of focus the magnets. Oh, I lost it. Darn. Oh, damn. Anyway, it killed about 7 people. Now, they had brain cancer, so it's hard to say it actually killed them, as opposed to sort of hasten their demise. But it did. It killed 7 people, and it did so largely because it has a software bug in it. All right? And these days, that's a relevant thing, which is to say, no. The only reason I'm worried about this is because if I don't get this right, we're going to run out of battery, and before the lecture ends. So that's why, and I'll be ordering one of these for before next lecture. Okay. So anyway, the idea here was a silly one. So it's this big giant machine. It would basically adjust these magnets to focus the beam on the right part of your brain. You are literally bolted into this. They actually drill and tap your cheekbones, and they sort of screw your head into the thing so that you can't move because they're going to focus this beam. Because what they're trying to do is heat up the tumor and kill it without killing the rest of your brain, which, as it turns out, is a challenging task to do. And the biggest problem they had was, so none of the engineers who developed it were particularly fast typers. And so what would happen is you had a screen where you had to enter in all this data on the patient, and then when you hit return, it would fire the beam. All right? So during the time that you were typing, it was moving the magnets to align the beam to the right place based on the data that you entered. Well, there was one guy in Chicago who could type upwards of 180 words a minute, and who was a tech who was working on it. And by the time he hit carriage return, the magnets were still moving. And so it took this beam and kind of wandered it all over the place, and that was what did it. Now, what was interesting about this was that it took them 18 months to develop the machine. It took them 3 years walking through the code to figure out why it had done this. All right, it was a subtle bug to do, and what I will teach you how to do in this class will mean that you will never, ever, ever do anything like that. All right, because by design you won't be able to. All right, and that's sort of one of the things we spend a lot of time on, is trying to get things correct by design ahead of time, see if we can find the bugs before they do any damage. But this is sort of, you know, I tell this as kind of a scary story, but I also tell it because these days software controls a lot of things. All right, and it controls a lot of things that are bigger and stronger than you are. All right, and therefore, you know, that happens. And, you know, I've got my collection of stories of, you know, when software kills and things like that, you know, because they're, you know, they make grisly tales and you'll remember them. So that's the thing. But it's important, all right, which is to say that, you know, what you're learning here isn't just an academic exercise. As you go on later and you start doing this thing, the things become important. All right. So at some point, you know, in your future, it's going to be your job to design something that, if it goes wrong, potentially will harm someone badly. Right, and so you want to make sure that you've done it right so that it doesn't go off. And, you know, conversely, you test a lot. Okay, so basically the idea is microcontrollers in devices are everywhere. All right, so we do that. We talk a little bit about number representations. Hopefully this is going to be review for all of you guys. This is awkward. So if I give you the number, you know, 3,857, you know, if you remember from, I believe it was first grade, you know, this is the ones column, this is the tens column, this is the hundreds column, and this is the thousands column, right? And so we do that in binary as well, all right? So, all right, I'm going to tempt fate. Yes. Okay. All right. So in binary, we have, for the computer, we have something that looks like, we'll write it in hex. This is a hexadecimal number, hexadecimal, which is base 16. And the reason we write it in, so this is called a byte. A byte represents 8 bits. A bit is a 0 or a 1. A 0 or a 1. Now, remember that ultimately when we get down to the end of this, what is the 0 or the 1? The 0 or the 1 is an electrical level. It's an electrical signal. And so what we've got is 0 really means that I am below some threshold, and a 1 means I am above some other threshold, and in between, you know, there's sharks in these waters, so stay out. Right? And that's actually a lot of the work is meant to sort of get you from one side to the other really, really fast and not spend a whole lot of time in between. Right? So we have a 0, we have a 1. That's the bit. Right? So our bit. Okay? And what we've got, if we take this, so A is 1010, and 5 is 0101. Right? So there it is. So we call this collection of 8 a byte. Right? And because someone was feeling clever, they refer to the 4 up here as a nibble, right? The high nibble and the low nibble. All right, so this would be the high nibble, and this would be the low nibble, all right, because it's the closer. And you'll see things that this is the least significant bit, and that is the most significant bit. And so this is sort of just general stuff. So let's take a look at this a little more carefully. So I have my 0x, A, well, let's do 3. All right, so this thing is, the numbers on this are 1010 and 0011. All right, so again, the LSB for least significant bit. By the way, if my writing sort of descends into chicken scratch and you guys can't read any of it at all, you know, tell me and I'll slow down a little. I try to accommodate. Yeah, it's chicken scratch? Yes, yeah, it catches both. It catches my voice and the thing, which is, and I will warn you that the best thing to do is to watch it at greater than normal speed. VLC will allow you to sort of accelerate. I find that I top out at about 187% of sort of normal speed. I can go a little faster, but it gets a little too hard to follow. And something really interesting happens when you watch it at faster than normal speed. First of all, the 2-hour lecture goes by in 1 hour and 15 minutes, which is kind of nice. But the second thing that happens is you find that it's going fast enough that you can't actually multitask. Because it turns out we can't multitask. We think we can multitask, but we in fact can't. And so what we do is we just lose concentration and do it. But when it's coming in fast, and the reason that this works is it turns out your brain is fully capable of processing audio much faster than you can create it. And so you can actually take in much more. And as I said, somewhere around 150 to 200% of normal speed, your brain will sort of lock in and say, wait, I have to pay attention because if I don't, I'm going to lose it. All right? And so you'll actually pay attention, which works pretty well. The other weird thing is what you'll see is what's on the screen, and you'll get my voice. And so if you wear it on headphones, I am in your head, which is, kind of weird. I'm not sure how my wife thinks about that, but, anyway. So, all right, this little one, that's a bit. All right, so a couple of things, definitions of terminology. We call a byte. Right? A byte is a collection of 8 bits. That means we have 2 to the 8 possibilities, or 256 unique things, and generally we count those as 0 to 255, or minus 127 to positive 128. And that's so we don't have, I think I got that right. Minus 128 to positive 127. Yeah, because we go negative 1 farther than we go positive. 128 to positive 127. And the reason is we don't need to count 0 twice. So that's why we get 1 more to the bottom. That's generally done with 2's complement. We have an int. So this in C is often referred to as a car. Right? Then we've got an int. Right, which is generally 16 bits, right, which is 2 to the 16 possibilities, which is 65,536. Right, often this is called a word. And then we've got a long, which is 32 bits, which is 2 to the 32, which is approximately 4 billion. And then if you really want, there's a long, we can go 64 bits and things like that. There's a question back there? Yes. We'll go over it, but yeah, the intake quiz is for your own edification. It's a wake-up call, all right? We'll get to that before the end of class. So now, one of the things that so that's number terminology. I think that's everything I wanted in that. All right. So the next thing we get to is modulo arithmetic. All right. So when we're working with 2's complement, all right, there are a couple of things in this class that will bite you that probably will not bite you in other ways. So one of the things is we often do 2's complement, which is if I have that number and I add 1 to it, what I wind up with is all zeros, plus a carry bit, which generally gets discarded. All right? So what winds up happening, the way I like to see this, is I imagine that it's a circle. Okay? Not the circle of life, but the circle of binary numbers. Right? And it starts at hex 00, right? And it ends at hex FF. So 00 is 0, and FF is -1. So it's -1, that's 0. So the numbers are going positive in that direction, and the numbers are going negative in this direction. And right here they meet at the most positive, right? So this is the biggest positive number, and this is the smallest negative number, right? The one that's farthest away from 0. Now the interesting thing is, the idea here is you can keep going around and around and around the circle, right? That's the beauty of modular arithmetic. If you keep adding to something and it overflows, that's okay because you just keep going around, right? You wind up sort of, so if you're here and you add a number, you wind up there, you get the same distance in the arc doing the addition and subtraction regardless of whether you go across one of those boundaries or not. That's what makes 2 complement work really well, which means if you're only interested in the difference between two things, for instance, you're counting the amount of time elapsed between a signal that came in, right? The only thing you have to worry about is, did I do a complete number of rotations around the circle that I didn't catch, right? Because if I go all the way around twice, then obviously I'm off modulo the full number of times I go around. Now, places that this is going to bite you. So this also means, for instance, that if I have 4 zeros, right, and I subtract 1, then I'm going to be at SF, right? And at first you're like, okay, that's a little weird, right, until you look at it and you see on the circle what's going on. By the way, I've got the pink dot to let you know what I'm pointing at. All right, now, places where this might bug you, all right, is if you do something like this. If you do car A equals 100, car B equals 5, and C equals A times B divided by 4, right, what should the answer be? 125, right? Show of hands. How many people think the answer is going to be 125? Oh, come on. You all think this. You just know it's a trick question. All right. So what's the actual answer? Anyone? No, you're not going to figure it out, but it's 61. All right? And the answer is, why is it 61? What happened? Right? Exactly. When I multiplied A and B together, right, I got 500, but 500 doesn't fit in 255. So I went all the way around. So A and B multiplied together in hex gives me 1F4. All right? But you said that's an 8-bit number because you told it it was a car, which meant that one, goodbye. All right? So you got F4, and then you divided F4 by 4, all right, which gives you the answer 61. So the way you get around this, by the way, is you have to temporarily promote one of them to a bigger value in order for it to do it, in order for it to do the computation using more bits, and then it'll collapse them back at the end. So how many of you have heard of casting in C? Right? Oh, good. This is getting better. Usually this is an alien concept. So if I do C equals int A times B divided by 4, I will get the right answer. All right? So the int right here is the cast. Yeah, so this is called a cast. All right? So this is called casting because I'm actually going to cast the car A into an int of greater bits, and then it says, oh, well, you're multiplying a 16-bit with an 8-bit. I need to promote the 8-bit one into another 16-bit, so I'm doing 2 16-bit multiplies. Right? Then I'll do the divide, and then I'm going to put the answer back into an 8-bit, so I'll truncate at that last step. Right? This, by the way, bites people all the time. Now, it won't bite us on the processor that we're using as much because it's a 32-bit processor, and so ints by default are 32 bits, and they're kind of hard to overflow. All right, but if you sort of do short things, you can get yourself in trouble fairly quickly. Okay, bit manipulation. So we have often in the case that we're doing things, we've got a microcontroller. The things that we're controlling with the microcontrollers are controlled by the state of the pin. The pin is represented by a register in memory, meaning that we're just going to have a number, and we twiddle a number, and a motor turns on, right? Or a fuse gets lit, or something goes kablooey, right? It's basically we have real things attached to the other side of this. So one of the things we have to work on is if we want to change things, right? Say I've got an 8-bit number that looks like 0000 and 0000. Right? So I would like to change that bit right there into a 1, would leave all of the others alone. All right? So how do I do it? What's that? Right? So yes, okay. So there's 4 things. We're going to go through how to do them all. All right. So there's 4 things I generally want to do with a bit. All right. I want to test a bit. That is, I want to know whether it's a 0 or a 1. What's that? There we go. All right. So we want to do that. We want to set a bit, which is forcing it to a state. a state of 1. We want to clear a bit, which is to force it to a state of 0, or we want to toggle a bit, which is to change its state. If it was a 1, send it to a 0. If it was a 0, send it to a 1. So test is it a 0 or a 1? I want to know. Set is force it to 1. Clear, force it to 0. And toggle is switch states. So if it was a 0, turn it to a 1. If it was a 1, turn it to a 0. And how we're going to do this, all right, is using our friends the masks and the bitwise operators. Right? So what we're going to do here, so if I want to, so we have our bitwise operators. So for instance, now in general, you say, well, if I want to make that a 1, just write the whole, write the register with FF. It'll be a 1. All right? But so will everything else. Right? And that's a problem. Right? Generally what I want to do is I want to leave the other ones unchanged and write only to, and change only the 1. So in this case, what I'm going to do is I'm going to AND it. So I'm going to, this one I want to write to a 1. All right? Because that's what I asked you to do. I want to do that. So I'm going to OR equal, right, the variable with this mask. And what that's going to do, it says, well, 1 or 1 is 1, 0, 0, 0, 0, 0, 0. 0, 1 is 1, 0, 0, 0, 0. So all I've done is changed that one place, right, but left all the other bits unaltered. Right? And that's sort of an important thing when dealing with embedded hardware. So the bitwise operators are AND, the OR, the NOT, which is a tilde. Be very careful, okay? There's also, right, do not use the exclamation point or bang. That is a logical NOT, not a bitwise NOT, right? So the bitwise NOT is the tilde is the complement of it, right? And lastly, the exclusive OR, which is the caret, all right? So, and what we would do, for instance, in this one, is we'll use pound defines to make our life easy and our code more clear and readable. Right? So we always want to use lots of pound defines. Right? So in this case, I might pound this define as bit 5 high, right, as hex 10, right? And if I look at that in binary, that's 0001, right, 0000. Right? So now, if I want to force that 1, right, say this is a variable, var, right? So I would do var or equals bit 5 high, like that. Okay? And what that would do is put us in. And what that will do is force that 1 there. So let's take a look at all of them. All right? So to test. All right, so if I want to test a bit, right, I just want to know if it's a 1 or a 0. Let's say here is my 1, and I want to know if that bit right there is a 1 or a 0. How am I going to do it? What's that? AND, right? So I'm going to say my variable and the mask. So in this case, it's going to be bit 1, bit 2, bit 3, so bit 3, right? Oh, well, in MPLabX we don't have the high, we just call it bit 3, all right? So there it is, my variable and bit 3, all right? And what's that going to be? How will I know if there's a 1 in there? A 1? Anything other than 0, right? If it comes back 0, so if this equals 0, right, then the bit was a 0. If it doesn't equal, if the bit's a 1, what's it going to equal to? It's something exact that you have sitting in front of you. Well, not 0, but no. Exactly. It's going to come back as bit 3, right? So the only thing, because all the rest are 0, right? All the rest are 0, except for that one. So when I AND them, all the ones that are outside that column, right, are going to get squashed to 0. The only one that remains is this one. So I'm either going to get back bit 3 or I'm going to get back 0. Yeah. Not directly. Not directly. You can use bit fields, all right, and you can sort of do a compound type where you can go into them, and there's some hardware things that allow you to look at it. So this is referred to as a, well, this is just a comparison, but generally no. There's some clever things you can do with unions and bit fields where you can separate it out, but if you actually look down the assembly, this is almost exactly what's being done. All right, so it actually does do it this way. Right, where it takes a look straight through. There are a few things where you can actually test a bit directly. All right, so that is to test a bit. To set a bit, right, that is going to be to force 1 to 0. How are we going to set it? We're going to do an OR equals with, let's say, bit 6. All right, so what that one's going to do is it's going to, so bit 6 is going to be 1, 2, 3, 4, 5, 6. Right, so what it's going to do is whatever was in here, right, previously is going to get carried through the operation. So let's give me 1, 0, 1, 0, 0, 1, 0, 0. All right, and I'm trying to force bit 6 high. Now in this case, bit 6 already was high, but it doesn't matter whether this was a 1 or a 0. Let's change it to that. All right, so it's going to preserve everything that was in there before and force the 1 in the spot where we wanted to. Right? So these are, by the way, we refer to these as masks. All right, and they're very useful. They're already defined for you, bit 1 all the way through bit 32. What's that? There's an underscore ahead of it. So they're already defined as this bit underscore number. Got it. Bit underscore 1 all the way down to bit underscore 32. Yeah. It's 1 to 32. I think it is. Yeah. Yeah, it is.
The autocomplete will tell you.
You'll learn to love the autocomplete in MP Lab. So control space, and it will sort of pop up all the things that match the pattern. So yeah, but I believe, yeah, because I believe it counts this as bit 1. So it's a little confusing considering C starts from 0 everywhere else, but yeah, there is an inconsistency there, but that's sort of the way it goes. All right, now to clear a bit. All right, so we've done test, we've done set, we want to clear. All right, so to set a bit was OR equals. To clear 1 is a little more complicated, right? So how am I going to clear it? And equal with not and my mask, right? So we use that's an and equal, right? So the and equal and the not of my mask is going to, so the not of the mask is going to flip all the bits, right? So if I have, let's do an example, let's say 1101, 0111, and I want to flip that bit. I want to force that bit to 0. All right. So what I'm going to do is I'm going to use my mask. My mask is going to be 0100, 0000. So there's my mask. First thing I'm going to do is flip all the bits. So that's going to change to 1011, 1111. And now I'm going to AND it, which is going to do that. Oops, that's a 1. It's a 0. That's a 0, and that's a 1. So the idea is, again, in that position where I wanted to, that is forced to a 0, and everything else is left untouched. All right? And then the last one, the toggle, the favorite of LED drivers all over the world. All right. So to toggle a bit, we're going to do what? Exclusive OR, right? Exclusive OR equals to my mask. So again, 0110, 1001, and I want to flip bit 2, right? I'm going to exclusive OR equal it with 0000, 0010, and that's going to come back, whereas So that's going to stay 0, that's going to stay 1, that's going to stay 1, that's going to stay 0. That one's a 1, that's a 0, that one's going to become a 1, and that one's still a 1. So I've preserved everyone across the top except for that one whose state I flipped. Right? And if I do it again, it'll flip back to a 0. So it'll keep flipping it one to the other and around. Okay. So all that hopefully is clear. You will be using that to sort of figure out which bumper is hit, for instance. All right. So you'll get the bumpers back. It'll give you a number. That number will have 4 bits in it that flip states when the magnets cross the sensors. All right. So on the roach, you'll need to sort of figure out which bumper was which. Pound defines are your friends. All right. So even if it happens to be bit 3 that you're testing for, go ahead and pound define. You can pound define another pound define, by the way, which is to say that you can have cascading ones. They're done recursively. Yeah. Pound define is part of the preprocessor in C, right, that allows you to do a text substitution. Okay. We use it a lot, all right, because what it allows you to do, for instance, is you can change bit 3. So normally what you would do, if you looked inside the code, you would see pound define bit underscore 3 looks like 1 shift 3, like that. Yeah. Maybe. Anyway. Yeah. Anyway, that's how you define it. And you say, okay, that's bit 3. It has the right pattern. I'm happy. And you say, but that actually turns out to be the front left bumper. And I'd rather know it as the front left bumper. So one of the things you can do is you can put pound define front underscore left underscore bumper is bit underscore 3. Right? And what it will do is it will sort of follow it, right? So everywhere it sees front left bumper in your code, the precompile will substitute bit 3, which will then substitute 1 shift 3. Right? It'll just keep doing the substitutions for you, right? Which means that from the code point of view, the computer knows what you're talking about, but from a code readability point of view, you know what you're talking about. So you can look at your code and you say, because frankly, trying to figure out, well, bit 3 is toggling up and down. What does that mean again? Whereas if you look at your code and say, okay, front left bumper toggling up and down, this I know, right? This means it's moving back and forth, and this is pretty straightforward.
It means you have it assigned one spot.
Yes, exactly. Right. It also means that if you decide, for instance, that you have it swapped and you pick up a new roach and for some reason that roach has the front left bumper as bit 4, you change it right here and you don't touch the rest of your code and the change percolates through it and matches it. So anything that is configuration type stuff that you're doing, sort of definitionally, use pound defines for those. That will help you out a lot. All right. Moving along. Questions so far? Nothing? Okay. Good. So I'll just sort of throw this out there, right, which is to say that if I don't get any questions or feedback from you guys, then it indicates to me that I'm going too slow and I'll speed up. Right? So if you find I'm going too fast, ask questions. It'll slow me down. So think of it as sort of, trying to trip up a horse that's running too fast. All right? So just, put some obstacles in front of it and I'll stumble. All right. So really quick question. What is a microprocessor? Anyone? Small computer. All right. I'll draw something that you might be familiar with. All right. So microprocessor is the part that does actually all the computing. In general, it has no memory, no I/O, and the computation is done on a single chip. All right. And these are sort of old definitions. They're not quite as done. So anyone, and probably no one here has ever heard of this, a microcomputer. What is the difference between a microcomputer and a microprocessor? All right. So I added I/O. That's the first thing. What else? Added memory. Okay. Added memory. Good. All right. And what about a microcontroller? What's that? Nope. Nope. No. A microcontroller is exactly the same as a microcomputer, except that Motorola patented the name in the 1970s and said, our microcomputers are different. They're a microcontroller. Interestingly enough, the ad campaign was so successful that nobody actually refers to microcomputer anymore. All right, basically, microcontroller has taken over the name. So there you have it. And in general, we have so nowadays we have amount of time. Oh, it is bit 0? Oh, okay. So we do start counting from 0 for the bit definition, so you know. All right. So in general, the kind of peripherals we see, we'll see things like timers, analog to digital computers, converters. Digital to analog is a little more common nowadays than it used to be. Pulse width modulation, communications, etc. All right. So now, one of the interesting parts about this is the components have gotten better. So we have our sort of big parts. So we have our ALU, arithmetic logic unit. By the way, if these terms don't mean anything to you, strongly suggest you take the half hour it's going to take to go through the cartoon guide to computer science that is on the website. It's a fun, kind of light book, but it will kind of bring you up to speed on all this very quickly, and it's a good read. All right, so the ALU or the CPU we have. Then we've got a couple of things that we need. We have our program memory. And our program memory we generally call ROM for read-only memory. We have our scratch pad, so our temporary memory. Memory. Now, this is referred to as RAM because it's pronounceable, but really, there's nothing, ROM is randomly accessible too, right? So the only, really this should be read-write memory, but ROM is kind of hard to pronounce, so it became RAM. And then we've got our input and output, which are generally pins on controller. Now, the really interesting thing is, most of you have probably heard of TTL logic, which means it goes from 5 volts to 0 volts. And it worked for a while. Most of the old microcontrollers are on a 5-volt rail. Run fine. And then someone came along and said, well, I can make a low-power version of this by dropping the rail to 3.3 volts between a 1 and a 0. And that works pretty well. In fact, the processors that we're using run nicely at 3.3 volts rather than 5, which is good. And then someone came along and said, you know what? I can do better than that. I can drop it down to 2.7 volts and still get it to work. Someone came along and said, I'll see your 2.7 and I'll go to 1.9. Yeah. Literally, they have to do it where the internal logic transistors have at the top. All right. So basically, there's a voltage rail within the core, and these days, a lot of the processors now go all the way down to 0.9 volts. All right, and often have an internal state that's at 0.9 volts because they can run at lower power. Now, this class you're going to learn a lot about a study in trade-offs, which is to say that if you get something, you almost always pay for it somewhere else, right? There's no such thing as a free lunch, especially not here, which means that anytime you see something where you say, hey, this is better, cool, right? Ask yourself the question of, what am I paying for it, right? Because you are. Even if you're not aware that you are, you're making that trade-off, right? So in this case, I get lower power, and in certain cases I can pack things tighter, which means I might even get more speed, right? But I'm going to pay for it somewhere. Where am I going to pay for it? You're close. So noise immunity, right? So noise immunity. All right, so if I have 0.2 of a volt noise on the thing, then, at 5 volts, 0.2 of a volt hardly matters, right? I've got a huge span. I've probably got 4 volts in between my high states and my low states. All right, 0.2 of a volt isn't going to come close. All right, at 0.9 volts, I'm on awfully thin margins here. Right, that means a little more noise, things get a little squirrely, right, and all of a sudden I start flipping random bits, right, and that usually is a bad thing to have happen in your code. All right, when that happens. Last thing I'll talk about before we end for today, since we did start a little late, but we're all right. So when I refer to the bitness of a microcontroller, right? So you've heard of an 8-bit, a 4-bit, a 16-bit, a 32-bit processor, a 64-bit processor now. So there are couple of things going on. So you've got two things. You've got your CPU, and then you've got an address bus that is going off, and then you've got two other pieces. So you've got your memory, and you've got your I/O, generally pins. All right, and then you've got a data bus that feeds the contents of the data. So the address bus, data bus. So the address bus tells you which location of memory or I/O to go grab, and then the data bus takes that data and feeds it back to the controller to do something with. Now, the question is, when you say I have a 16-bit microcontroller, right, which one are you referring to, the address bus or the data bus? So I'm hearing a loud consensus for address bus. Yes? Show of hands, address bus? Okay, you're all wrong, right? It's the data bus. All right? The address bus, so even a 4-bit microcontroller might have a 24-bit address bus, which means it can address a huge amount of memory, but it can only come in 4 at a time. All right? So the bitness always refers to the data bus. All right? So that's when you say it's a 16-bit, so a 64-bit computer means it can grab 64 bits at a time out of any location in memory and get it to the CPU in essentially one clock cycle.